Have you ever wondered how we know exactly where we are on Earth or how we can predict the impact of a climate event before it happens? The answer isn't magic, but a powerful toolbox. Welcome to this journey through the fundamental tools of geography, the true magnifying glasses with which we decipher the world. Today we will reveal the secrets of cartography. We will explore the wonders of geotechnology and learn to read between the lines of statistical data. Whether you are curious students, passionate teachers, or simply minds hungry for knowledge, prepare to discover how these disciplines are not just subjects of study, but living, breathing tools that help us navigate and understand every facet of our planet, from the smallest road we travel every day to the great global changes. By the end, you will have a clear vision of how these disciplines intertwine to give us a complete and dynamic picture of our world. Geography, my friends, is much more than a list of capital cities or memorizing rivers and mountains. It is a dynamic discipline, a science that studies the Earth's surface, its characteristics, its inhabitants, and the phenomena that shape it. But how does it do it? Simple. Using a series of tools that allow it to collect, analyze, and interpret spatial and socioeconomic data. Think of a doctor without a stethoscope or an engineer without his set, square, and compass. In the same way, the geographer needs his tools of the trade to be able to carry out his work with precision and depth. These tools are not just technical aids, but true extensions of our intellect capable of transforming a mountain of raw data into usable knowledge, into profound understanding. Their main function is precisely this: to give us the ability to read the world, to predict trends, to plan interventions, to understand why things are the way they are and where they are. From ancient hand-drawn maps to cutting-edge spatial analysis software, each tool plays a crucial role in the vast landscape of geographical knowledge. And today we'll explore them one by one. We'll start with the most classic and perhaps iconic of geographic tools, cartography. Cartography is the art and science of representing the Earth's surface, or parts of it, on a flat surface, whether a sheet of paper or a digital screen. Imagine having to fit an entire world or a gigantic portion of it into a handy format that can fit on a desk. This is the task of cartographies, and to do so it uses some fundamental components. The first and perhaps most crucial are geographic coordinates. Think about it. How can we say exactly where any point on the Earth's surface is without ambiguity? Near the sea or behind the mountain isn't enough. We need a universal reference system. This system is based on two values, latitude and longitude. Latitude measures the angular distance of a point from the equator, either north or south. Imagine horizontal lines surrounding the Earth parallel to the equator. These are the parallels. The equator is at 0 degrees dr, the North Pole is at 90 degrees north, and the South Pole is at 90 degrees south. Longitude, on the other hand, measures the angular distance of a point from a prime meridian, the Greenwich meridian, either east or west. Meridians are vertical lines running from one pole to the other. Greenwich is the prime meridian. With these two numbers, latitude and longitude, we can uniquely identify any point on our planet with astonishing precision. It's like the exact address of a house, but for every corner of the Earth. But there's a problem. The Earth is more or less a sphere. How do you represent a curved surface in 3 dimensions on a flat sheet of paper which only has 2 dimensions? This is where the cartographic projections. This is the heart of the problem with cartography. It is physically impossible to flatten a curved surface without deforming it. Try peeling an orange and spreading the peel on a table. It breaks, it deforms, it's no longer smooth. The same thing happens with the Earth. Map projections are mathematical methods for transferring points from the Earth's spherical surface to a flat plane. The result, every projection inevitably involves distortions. There is no perfect map. Every projection distorts something: the shape of the continents, their area, the distances between places or directions. For example, the famous Mercator projection, very useful for navigation because it maintains directions, enormously enlarges the lands near the poles, making Greenland appear as large as Africa, when in reality it is 14 times smaller. Other projections try to preserve areas, such as the Gall-Peters projection, others distances. The choice of projection depends entirely on the purpose of the map. There is no best one, just the one best suited to the intended use. Finally, we have the reduction scale. Imagine you want to draw your city on a sheet of paper. You can't draw it life size, you have to scale it down. The reduction scale is just that, the ratio between a distance measured on the map and the corresponding distance in reality. It is expressed as a fraction, for example, 1/10,000. This means that 1 centimeter on the map represents 10,000 centimeters or 100 meters on the ground. Maps with large scales, such as 1 by 1000 or 1 to 5000, show a small area with lots of detail, useful for planning a walk. Maps with small scales, such as 1 or 1000,000, show a very large area with little detail, ideal for planning a trip between continents. Scale directly influences the level of detail that can be represented and consequently the practical use of the map. Now, if cartography gives us the ability to represent the world, geotechnology allows us to interact with it in ways that only a few decades ago would have been science fiction. These tools represent a quantum leap in geographic analysis, offering powerful capabilities for collecting, processing, and analyzing spatial data. They are the engine that powers modern geography, making it an incredibly applied science and relevant to nearly every aspect of our lives. The first and perhaps most revolutionary of these tools is the GIS, or Geographic Information System. Imagine not a single static map, but an intelligent system, a highly advanced software capable of managing, analyzing, and visualizing an incredible amount of geographic data. The power of GIS lies in its ability to overlay different layers of information on the same territory. For example, you can have one layer with roads, another with buildings, a third with population density, a fourth with the distribution of shops, and so on. Each layer is a source of georeference data that is linked to precise geographic coordinates. By combining these layers, GIS can answer complex questions. What is the shortest route for a truck making 10 deliveries in the city, avoiding roads with heavy traffic and weight restrictions? Or where would it be most logical to open a new supermarket to reach the greatest number of potential customers, considering existing competition and access routes? GIS doesn't just show you data, it analyzes it to find relationships, patterns, and trends that would be invisible to the naked eye. It's like having a superbrain that thinks geographically, allowing us to make more informed decisions and understand complex phenomena, from urban planning to disaster management. Then there is GPS, the Global Positioning System. I think almost all of us use it daily on our smartphones without thinking too much, but how does it work? GPS is a network of satellites that orbit the Earth, constantly transmitting radio signals. A GPS receiver, like the one in your phone, intercepts signals from at least four of these satellites. By calculating the time it takes for the signals to reach it and knowing the exact position of the satellites, the receiver can determine its precise position on Earth with an accuracy of a few meters or even centimeters. It's a seemingly simple technology, but its applications are endless. From road navigation to precision agriculture, guiding autonomous tractors, from monitoring tectonic movements to mountain rescue. GPS has literally put the exact location of our planet in the palm of our hand, revolutionizing the way we orient ourselves and interact with space. Finally, remote sensing. This tool is a bit like having the eyes of a giant observing the Earth from space or from great heights. Remote sensing uses sensors placed on satellites, satellite imagery, or on airplanes and drones, aerial photography, to acquire information about the Earth's surface without direct physical contact. These sensors record electromagnetic energy reflected or emitted by the Earth at different wavelengths, which are invisible to the human eye. Every object on the Earth's surface, water, vegetation, concrete, bare soil, reflects and absorbs light differently. By analyzing these spectral signatures, scientists can identify, map, and monitor a wide range of phenomena: forest coverage and health, land use changes, such as desertification or urban sprawl, ocean surface temperatures, glacier melt, and even the spread of pollutants. Remote sensing is extremely useful for economics and technology because it provides global scale, real time data, which is essential for environmental monitoring, agricultural planning, emergency management, and climate change analysis. It allows you to see patterns and trends over vast areas that would be impossible to detect from the ground. The combination of GIS, GPS, and remote sensing is a symphony of power. A satellite image, remote sensing, can be uploaded into a GIS for analysis, and GPS position data can be used to verify the accuracy of satellite data or to gather new information in the field. These geotechnologies have crucial applications in many sectors, from urban planning, where they help decide where to build new infrastructure or manage traffic, to natural resource management, monitoring the health of forests or water availability. They are essential tools for analyzing the territory, for understanding how our environment is changing and how we can better manage it. But the tools of geography do not stop at the visualization and analysis of physical space. To truly understand the world, we must also understand the human, social, and economic dynamics that shape it. And this is where statistics comes in. If maps show us where, statistics tell us how much and why. In geographical analyses, statistical data are essential for understanding socioeconomic and demographic dynamics. Imagine you want to study the distribution of wealth or education across different regions. You can't just look at a physical map. You need numbers, you need indicators. The essential skill in this field is knowing how to correctly read and interpret graphs, tables, and socioeconomic indicators. It's not enough to look at a number, we need to understand its context, its implications, and its trends. Their purpose is precisely to allow us to interpret trends, identify regional inequalities, and understand the connections between economic, social, and environmental factors. Among the key indicators, some stand out as global benchmarks. The first is GDP, the gross domestic product. This indicator measures the total value of all final goods and services produced within a country's borders in a given period, usually a year. It's the most common and direct measure of a nation's economic wealth. If GDP grows, the economy expands. If it decreases, the economy contracts. Geographers use it to map the distribution of economic output, identify richer or less wealthy regions, and study how economic activity is concentrated or dispersed across the territory. However, GDP alone doesn't tell the whole story of a population's well being. A country may have a high GDP, but experience significant inequality or a low quality of life for many of its inhabitants. And this is where the comes in. HDI, the Human Development Index. Developed by the United Nations, the HDI is a composite indicator that goes beyond the mere economic aspect. Consider three fundamental dimensions of human development: life expectancy at birth, an indicator of the general health and well being of a population; education, measured by average years of schooling and expected years of schooling; per capita income, based on GDP per capita but adjusted for purchasing power to reflect the standard of living. By combining these three factors, the HDI offers a much more comprehensive and nuanced view of human well being than GDP alone. Two countries with similar GDP can have very different HDIs if one invests more in health and education for its population, showing that development is not just economic growth, but also and above all, the development of people's capabilities and opportunities. The HDI allows us to compare the level of development between different regions or countries, identifying where investments in education and health are paying off and where instead there are still large gaps. The real magic happens when this statistical data is combined with spatial information. Put together the population density map (GIS) with the HDI data for different areas and a much richer picture emerges. You will observe how regions with a low HDI tend to concentrate in certain geographical areas, perhaps related to environmental factors or the lack of infrastructure. This combined analysis is powerful because it allows us to understand the complex relationships between territory, economy, and society. It helps us identify the root causes of inequalities, plan targeted interventions, and monitor the effectiveness of policies. This is how modern geography becomes an indispensable tool not only for describing the world, but also for changing it for the better. These tools, from the paper map to the most advanced geotechnologies and statistical analysis, are not separate entities. They are threads that intertwine into a complex and fascinating fabric, allowing us to read, interpret, and even anticipate the dynamics of our world. They offer us a unique perspective, a vision that goes beyond the single detail to embrace the whole picture.